Okay, so for today, we're going to go through current of electricity. So current electricity is like the follow-up from static electricity, but this is also the base or the foundational topic for the next one, which is DC circuit. So let's go through this in detail. If your foundation for this is good, actually what's going to happen is that it's going to help you quite a fair bit when you're dealing with chapter 16, right, regarding whether current is splitting or voltage is splitting whatsoever. If you know the base of it, it's going to help a lot. Right, so I want to really go through the textbook, some of the details inside here. Okay, so let's start. Okay, so 15.1 electric current. We're going to define the term current and state its SI unit. We're going to differentiate between the two types of current flow. Right, it is about current flow. Okay, we got the conventional current and the electron flow. Next, we're going to learn how to apply the formula charge equals to current times time. This is actually equals to Q equals to I times T. And last one, drawing electric circuit. I think this one, we won't go through too much in detail, but it's actually not so difficult. It's just a build up from your primary school details. Okay, so let's start. What is the electric current? Okay, now, so this part here is just describing on static electricity. We know that atoms or objects become charged, okay, due to the electrons being removed or added. Now, key thing here is that when the electrons start to flow through the path or to the object, okay, this one is actually where a current is produced. Okay, so when a charged object is provided a conducting path, electrons will start to move and flow. Okay, and when it starts to move and flow, we say that electric current is produced. So when charges move, that is when we say a current is produced. Okay, so charge move equals to current flow. Now, so after we are a bit more steady with what exactly is a current flow, which is the movement of charges, okay, we go into the idea of how can the charges move. Okay, so first one we have is this. Okay, the flow of positive charges, we call it conventional current. It actually flows out from the positive terminal and it flows into the negative terminal. So the current flow from the positive to the negative side, this kind of movement, okay, the flow of positive charges from the positive terminal to the negative terminal, we call this conventional current. And this is the one that we will always use, okay, when we go through our circuit. Okay, a lot of the things that we have created is actually based on conventional current. In actual fact, in real life, it's actually not the positive charges flowing. In real life, it's actually the electrons that are flowing. Okay, in real life, actually, electrons are the one that's flowing, and it actually flows from the. Let me use red color to show. Red color to show the conventional current since they already used red already. Right, then electron flow, I'm going to use blue color. So electron flow is this direction, the blue color one. From the negative terminal, it flows to the positive terminal. So conventional current, electron flow. Some questions, sometimes easier ones, will just ask you indicate on the diagram, okay, the conventional flow, okay, or the conventional current. So all you need to do is just draw this arrow, right, to show that it comes out from the positive terminal into the negative terminal. Sometimes they might ask you to draw the current flow for electron flow, then you will need to draw in the other direction. So just take note of this. Okay, it has come out before, but very rarely, okay, but it has come out before. So take note. So conventional current is a direction opposite to electron flow. So conventional current from positive to negative, and from positive to negative, whereas for electron flow is negative to positive. So take note of this. Okay, so in this book, take note, in this book, the term current refers to conventional current. So as I mentioned, the whole of the book is using conventional current as the main type of current to elaborate on all the various other things. Okay, so just take note of that. Okay, so how exactly do you measure electric current? So since current consists of moving charges, okay, you want to measure charge moving, right? So what they do is they actually measure the amount of electric charge that passes through a conductor per unit time. So to measure the charge moving, They actually measure how many charges pass through a conductor per unit time. So how many charge passing through per unit time. Okay, so this is current. So this is the equation here. I equals to Q over T, where I is current, Q is charge, T is time taken. Do take note that time must be in seconds. Okay, some questions I will give you in minutes or in hours. Please remember to convert it to seconds. So this is the part where it gets a bit confusing. Current, the symbol is I, but the SI unit is actually ampere. The SI unit for current is actually ampere. So you can see the symbol is I for current, but the SI unit is actually ampere. So most people get confused with this. They thinking, why is it I equals to Q over T? Why not A? Why charge is Q? Why charge is not C? So you must be able to differentiate the symbol for the quantity. So I say again, symbol for the quantity. Okay, quantity could be like your current, could be like your charge, okay, can be time. So that's the symbol for the quantity. These are quantities, okay, physical quantities. You need to be able to differentiate them, okay, between symbols for quantity versus symbols for SI unit. So SI unit, example, ampere. Ampere is the SI unit for current. Then you have charge. Sorry, charge is not the SI. The SI unit is actually Coulomb, right, which is capital C. Okay, and then time. Sorry, SI unit time is seconds. Yes. So there is a difference between the symbol for the quantity and the symbol for the SI unit. So you must be clear on this. Be very familiar with it. Otherwise, you tend to make mistakes. Okay. So how to measure electric current? They actually use this instrument called the voltmeter. Most of you would have seen this in your practicals already. Okay, so take note, ammeter should be connected in series to the rest of the circuit. Okay, so you can see here, ammeter is in series to the whole circuit here. So this one, you can refer to this diagram. Next thing, the current should flow into the ammeter through the positive and leave through the negative. So actually, positive connect to positive, negative connect to negative. This one is more for your practical knowledge. Right? This one here is both for theory and for practical. So just take note of this. Okay, so ammeter connection, that's one. Next thing, the formula is the second one. And the last one is really understanding what is electric current. It's the rate of flow of electric charges. So this has come out for definition also. So just please take note of it. Okay, a worked example, this is good for you to look at, okay, in terms of how to calculate current. So Coulomb, 2 minutes, take note, let's convert to second. Okay, I will not go into further details into this. You can see the solution. 15.2 is another one for you to look through. Okay, so in terms of applying the formula, it's actually not too difficult, especially for combined science. It's quite direct most of the time. Next, drawing circuits. Okay, so normally, if you're able to draw the circuit, it will definitely help you to understand how things goes. There are a few components, definitely in every circuit. First is the power source. So generally, it's a cell or battery. Okay, there's always a power source. This is the one that actually push the charge out. So you need the power source to push the charge out. What they say, drive the charge. Next thing you need is the load. The load is actually a bulb or resistor or any component, okay, that converts energy to another, converts electrical energy to another form. So a bulb actually converts light, the electrical energy into light. Okay. Now, sometimes a load can also be a resistor. Now, so in terms of resistor, how is it actually a load? So for resistor, it actually converts your electrical energy into heat or thermal energy. So resistors actually converts the electrical energy into heat. So just take note of that. Next thing, you not only have your cell, you not only have your load or your power source, your load, you also need conductor to connect the whole circuit. So generally, we talk about conductor, we're talking about the wires. And last one, typically in all your circuits, you should have a switch, okay, to control the circuit whether it's open or closed. So take note, the word is open and closed, not switch on, switch off your circuit. Is to open the circuit or to close the circuit. Okay, now next, 15.1 shows all the circuit symbol. So I'm just going to go through some of the important ones that you definitely need to know. So switch, typically I'll use the one with the circle instead of this. A cell and a battery. Now a battery, you realize the difference between a cell and a battery is that if I got two or more cells connected together, I get a battery. So one cell is just a cell alone. If I got two or more cells connected together, I actually get a battery. Okay, so take note of that. DC power supply, AC power supply. The difference between these two is that DC, the current, the positive and negative terminal is fixed. Whereas for AC power supply, alternating current. Okay, this is actually the current actually flowing in different, alternating. The positive and negative terminal actually alternates between the two sides. So it flows from the left to the right. Next thing, it flows from the right to the left. So AC, that's what AC means, alternating power, alternating current. Okay. Light bulb, definitely will need. Potentiometer, this one you tend to see it more for pure. Okay, but this one will need. This one, you also see it for pure. Combined, you don't really see it. For wires connected, normally we'll use this. Wires crossed, that means they don't touch each other. They just go over one another. We seldom use this. Okay, so not really. This one, yes. This one, yes. Fixed resistor versus variable resistor. Do take note, variable resistor has another name called rheostat. Okay, so it's a fixed resistor. You draw that out first, but then you put an arrow through it to show that you can adjust. Fuse, definitely need in under practical electricity. Coil of wire, this one for magnetism. Transformer, this is more for pure. Semiconductor diode, this one more for pure. Galvanometer, this one more for pure. Okay, galvanometer actually just measures in which direction does the current flow. So it's just, but it doesn't measure the amount of current. Ammeter, definitely we need. Voltmeter, definitely we need. Two-way switch, haven't really seen it coming out yet. Earth connector, yes. Okay, earthing, so this is under practical electricity. Capacitor, okay, this one. Thermistor, yes, pure likes to come out with this. So I will take pure. A bell, okay lah. This one, actually pure combine both, so you sometimes will see lah. But when you do see this, okay, most probably in the diagram or in the question, they will describe telling you that that's a bell. They won't leave you to die just. Okay, but it's a very nice looking mushroom lah, a bell. Okay, now let's go on. Interpreting circuit diagrams. Okay, now under this part here, I need you to be aware. It may look very simple. It is simple, but there is a concept here that I need you to understand. Okay, so for switch here, okay, generally when the switch is open, it breaks the circuit. Okay, sorry, it breaks the circuit. Okay, so when there's a switch, when the switch is open, it generally breaks the circuit. It means that current cannot flow through it. So that's what the switch does. So sometimes breaking a circuit can occur due to loose connection, missing or broken wires. This one, okay lah, good to know lah. Now, this is the one that I need you to take note. This is what we call a short circuit. If you look at the diagram here, okay, generally we use current as flowing off from positive, conventional current. So flows out from the positive, go through the ammeter, goes through the switch, comes here. Now, there's two paths that the current can flow. I'm going to use orange for one of them. I'm going to use green for the other one. Like this green hard to see. Let me use another green. Brighter one. Let's use the lime green, okay? Lime green, yeah. Right, there's two paths which the current can flow. Now, take note, if I have a wire like this, the wire, we tend to say that it has negligible resistance, negligible resistance. So in real life, wires obviously have resistance. But in your theory, in physics, we assume that wires have negligible resistance, which is like zero resistance. Okay, so when the current comes to this particular point over here, it can flow in both directions. Okay, and flow through the light bulb and flow through the wire X. However, because there's no resistance on wire X, all the current will flow through this way. All will flow through this way and come this way. So this is actually how the current will be flowing in this. Oh no. It is actually how the current is flowing in this particular diagram. It will bypass the light bulb because the wire here has zero resistance. So imagine zero resistance versus some. Obviously, all the current will flow through the zero resistance. Okay, and when we have a something like this, where there's a bypass, we call this short circuit. So short circuit is a term that you need to know, okay, and it's actually introduced over here in current electricity. So just take note of this. Okay, this one, obviously, when you seldom go through the textbook, you won't really see this. So a lot of people tend to ask, what is a short circuit? So this one actually gives quite a good example. A short circuit is actually where the current bypass the load. Okay, what you realize that in a short circuit, the current bypass the load. So just take note of that. Okay, sorry, green color very ugly. Let's change to blue color. Okay, so this one, okay, just take note of that, especially for this short circuit. So what we have gone through, we learned that current is the rate of flow of electric charges. Okay, and the formula I equals to Q over T. Next one, we learned that the SI unit of current is ampere. Okay, and then there's two types. There's two directions which current can flow. One is called the conventional current. It's the flow of positive charges from positive to negative. Whereas electron flow is the flow of negative charges. To be exact, is actually a flow of electrons. Okay, in opposite direction. What does it mean? It means from negative to positive. So that's for current here. So to sum up, this is the key idea behind what current is. So take about 1 minute. Now pause. Think through what we have gone through. Okay. Absorb everything. Okay. Then after that, I'll go on to the next segment. Okay. So we will pause here for a while. Okay. Next one. Okay, so we are done with current. Now we're going to go on to this thing called the electromotive force, or what we call potential difference. Now, these two things uses the same concept. I should say uses the same unit, which is volts. Then later on we'll go into it. Okay, but they are different. They are different. So let's, before we go into EMF and potential difference, okay, let's go into really some of the key basic ideas first. Okay, now volt is the measure of for the electrical properties of EMF and potential difference. So volt is a measurement for EMF. Volt is a measurement for potential difference. Now, what does EMF and potential difference do? So EMF and potential difference cause the charge in the circuit to flow. Cause the charge in the circuit to flow, cause it to move. Now, what's the idea here? So I thought here is actually quite a good one to illustrate to you. So water doesn't flow through the pipe on its own. So if I got a pipe here inside filled with water, you realize the water will be stagnant. It will not flow at all. Okay, so no flow. Whereas if I got a pump here, imagine this is the positive, this is the part where the water is pumped out. This is the part where the water is coming back in. So I pump out the water here, so it causes the water to move, right? So the water will flow in this direction because of the water pump. Okay, this pressure difference. So actually, what your water pump does is actually applies a pressure to the water, causing it to move. This pressure difference will make the water move around the pipe. Okay, so what does it tell you? It tells you that you need EMF or you need potential difference in order for the current to move. It functions like the water pump. So EMF and potential difference function like the water pump. It causes the current to move. Okay, so now first things first. An electrical energy source is needed to move the electric charges around circuit. So the keyword here is electrical energy source. So this electrical energy source pumping, we call it the EMF. So the pumping action by the source, okay, is called the EMF. So I want to emphasize on the word source. So EMF is only used for electrical source. Okay? I need you to think of that. So EMF of an electrical source is the work done by the source, in driving a charge around a complete circuit. So it's driving a charge around a complete circuit. Because why? EMF is for the source. So if I were to draw a battery like this for the light bulb, okay, for the switch, let's close the switch. Okay. So this battery here will definitely have an EMF. The EMF is like a pump. Okay? It helps to drive the charge. Okay? So all your batteries are like a pump to push the charges out and make them move. Okay? So because of its definition here, you know that EMF, which is a small e, well, this weirdly thing is called actually an epsilon, okay, is equals to work done over charge. Now, for those of you in my class, you realize that don't like to use W because work done is a form of energy. As such, I tend to write it like this. So instead of E equals to W over Q, I'll write epsilon equals to energy, this capital E over Q. So you must be able to differentiate now. This is actually your EMF is equals to E over Q. So to make things simple for everybody and to not confuse over it, EMF is equals to the energy required to push the source around the whole circuit divided by the charge, number of charges. Okay, so this is what I tend to remember. So this E represents energy in joules. Right, joules. So the SI unit for EMF is actually joule per coulomb. Okay, but this one sounds damn cheap, right? In actual fact, we simplify it to volts. So joules per coulomb, J per coulomb, is actually volts. Okay, now, so there are many types of electrical energy source. A common one is actually a dry cell, which is actually just a cell. So what you're going to draw, it looks like this. So this is your typical cell. Okay, as mentioned here. So do take note, the dry cell always has a positive and a negative terminal. The longer one is positive, the shorter one is negative. Okay? Next, what is potential difference? So EMF is the work done to drive a unit charge around the whole circuit. What is potential difference? Okay, so when a dry cell connects a light bulb, the bulb converts the electrical energy provided by the dry cell to light thermal energy. Okay. For each coulomb of charge passing through the light bulb, the amount of electrical energy converted is called potential difference. So work done to drive the charge around the circuit is EMF. So EMF, this is to drive, okay, so sorry, energy to drive a charge around the whole circuit. Potential difference, PD, okay, is actually the energy converted. Okay, energy converted. Okay, I'm actually using here energy converted, okay, to other forms of energy. Per charge. Right? So you can see here, drive energy to drive a charge around the whole circuit. Energy converted to other forms of energy per charge through the component. I miss out this part. So one is around. So EMF is normally referring to the battery because it's driving the charge around the whole circuit. Whereas when we talk of potential difference, what we are looking at is energy converted to other forms of energy through the component, or energy converted to other forms of energy. Okay, let me rephrase this. To other forms of energy by a component per charge. Okay, so I purposely put this side by side so that one on top, one below, so you can draw a difference between both of them. So both is about energy and both is about a charge. However, one is around the whole circuit, The other one is specifically for a component. Okay, so what's the formula? V, which is the potential difference, is equals to work done over charge. So those of you in my class, you realize Cher don't like to write this. Cher will always convert this to V equals to E over Q, whereby this E is actually energy. Okay, so energy converted to other forms of energy per charge. So once again, you realize SI unit is the same for EMF, is actually volts. So both EMF and potential difference have the same units of measurement, which is volts, which is also the joules per coulomb, right? Joules per coulomb. Okay? So just take note of this. Okay, so potential difference is like the pump. Okay, like pump. Now, so how do we measure EMF and potential difference? So we actually use this instrument called the voltmeter. We can actually measure the EMF of a cell using the voltmeter. We can also measure the potential difference across a component. I need you to take note of this. Voltmeter must be connected in parallel with the component. So generally, whenever I tell my students to use the voltmeter, just prepare your voltmeter in like this, with two claws. Okay, this is to one side, this is to the other. Sorry, I just put two dots. So you take your voltmeter, you plug it at two different points to measure the difference in the potential. Okay, to measure potential difference. So you can see, looking at this circuit diagram here, what you realize that the voltmeter is put here. It measures the potential difference from here to here. So this is before it goes through, current flow there, right? Current flow, yeah? So this is before it flows through the light bulb. This is after it flows through the light bulb. So if I know how much energy each charge have before, and I know how much energy each charge have after, I can actually find the potential difference and find the voltage. Okay, so voltmeter is always measured, or it's always connected in parallel to the whole circuit. Okay, so I think that's about it. So generally, if you look at the work examples here, once again, it's using the formula B equals to E over Q, or you will see a small epsilon equals EMF equals to E over Q. Right? Both is the same, energy per charge. So this is for EMF, this one is for potential difference. So you realize both the formulas is sort of like the same. Okay? So don't be too confused about them. Okay, they're actually just almost like the same thing. Okay? So that's for EMF here. So key ideas as a summary: EMF is the work done by a source in driving a unit charge around a circuit. So work done in driving a unit charge around a complete circuit. Potential difference across a component is the work done to drive a unit charge through the component. So around a complete circuit versus through the component. So this is the difference here. And you use red color to underline for you, or to circle for you. Okay, that's the difference. Similarity is both of them uses the same SI unit, which is volts. Okay. So how to distinguish? As mentioned, one is around the complete circuit, one is through the component. And question 2, you can go and try on your own. It's not really too difficult. Okay, it actually combines your current knowledge with the current one. It combines the 15.1 knowledge and your 15.2 knowledge together. So you can go and try it out. Question 2. Okay, so that's for potential difference. That's for EMF, which is the same as volts. Okay, which is the same as volts. Next one, resistance. So we talk about voltage, we talk about current. Right, next we're going to talk about resistance. So what exactly is resistance? It is actually a measure of the opposition an electric current experiences. Right, it's a measure of the opposition an electric current experiences when it flows through the. So the greater the resistance means that the greater the opposition towards the current. Okay, and what is the exact definition? It's actually a ratio of the potential difference to the current flowing through it. This can be simplified into this formula: R equals to V over I. Ratio of the potential difference to the current flowing through it. Okay, so this is one key idea I need to take note. The higher the resistance, the smaller the current passing through it, because the higher the resistance, the greater the opposition that the current experience, and hence the current amount will be lesser. So what's the SI unit for resistance? It's actually ohm, this sign over here. Okay, so that's for resistance. And then look at how you can apply the calculation. I think V equals IR shouldn't be too much of an issue for many of you. And I think this should be quite okay. Now for resistors, there are actually two kinds. One is called a fixed resistors, one is called a variable one. So fixed resistors, it has a fixed value. Okay, fixed value. So the resistance is fixed, it's a fixed value. Whereas the one that we have called is called the variable resistors. What they have is a resistance that can be varied. So variable value. Okay, the value can change. So another name for variable resistor, as mentioned, is actually also rheostat. So just take note of these two terms, variable resistor and rheostat. They are the same thing. Okay, so how to draw them? Okay, just recap. So for resistor, it looks like this. For variable resistor, it looks like this with the arrow flow going through it. Okay, next, how do we measure resistance? So generally, you don't. Okay lah. I mean, technology-wise now it's so good, right? You can just have a what we call an ohm meter. Ohm meter. Okay. What it does is measure resistance. So you can directly measure the resistance. But of course, in your textbook, we teach you the basic way. The basic way is you find the voltage, you find the current, the ampere, then you use R equals to V over I. You can find the resistance. But in real life, there's the device now that can actually measure your resistance. We call it the ohm meter. Okay. So, yep. So that's it. Okay, this one here, okay, just you can read through. Practical, you want to read this through before practical, but this is a very simple one. Maybe pure might want to read this, but combined science, I just follow the experiment. Okay, next, let's go on. Okay, look through the examples. I'm going to go through them. Okay, key ideas. The resistance of a component is the ratio of the potential difference across it to the current flowing through. That's just the idea of R equals to V over I. SI unit, ohm. Okay, to find the resistance in a circuit, we normally will use an ammeter and a voltmeter so that we can get V and I, then we take R equals to V divided by I. Okay, but of course, as I mentioned in real life, there's this thing called the ohm meter, or they use what we call a multimeter. The multimeter, you can just turn the thing, turn the thing. It can become ammeter, it can become voltmeter, it can become ohm meter. Quite interesting, the multimeter. Okay, so this one, those of you interested to do engineering, interested to go into electrical field, the multimeter is your best friend next time. Okay, so that's for resistance. So we have gone through I, which is current. We have gone through V, which is EMF or potential difference. We have gone through R, which is resistance. And how is these three values linked up together? We know that R equals to V over I. Okay, or the other way is I always tell my student V equals to Ri. Okay, let's not carry on with this. Let's go next. Okay, resistivity, last part of this whole chapter already. So what exactly is resistivity? Okay, before we go into all this, I need to take note of this over here. This is more for your practical or for your practical. So a large current may heat up the conductor, and an increase in temperature actually causes an increase in resistance. So I need you to take note of this. When the temperature of a conductor increases, it actually increases the resistance. Okay, so large current can heat up. That's why in the end, since large current heat up and an increase in temperature cause an increase in resistance. So generally, whenever we want to do experiment, we'll make sure that we use low currents. Of course, in your experiment, you can't adjust the current, but I need you to remember that if you keep letting the current flow in the circuit will heat up, it will cause the temperature to increase, Okay, cause the temperature increase, resulting in increase in resistance, and hence your overall result may be affected. So whenever you're not, so practical tip, when circuit is not in use, open the circuit, okay, by controlling the switch. Okay, so besides temperature affecting the resistance, there are three other things that can affect the resistance. One is the length, one is the cross-sectional area, the other one is the type of material it's made of. Okay, so let's go into some of the basic stuff first. Relationship between resistance and cross-sectional area. So wire P and Q, same length, made of same material. What happened is that the cross-sectional area of P, so you can see the cross-sectional area of P here is larger than that of Q. So experiments have shown its resistance decrease proportionally when the cross-sectional area is increases, right? And hence, in other words, resistance R is inversely proportional to area. Okay, so we get this. What does this mean? That means, right, find the resistance. Okay, find the resistance. Okay, this one later we'll go through some examples. I don't want to go through it. I just need to take note of this thing here. So when R increase, when A increase, R will decrease. A is your cross-sectional area. Next one, relationship between resistance and length. Right? If they have the same cross-sectional area, same material, but this guy here is longer, wire S is longer, wire T is shorter. So when they did the experiment, they realized that the resistance and the length is proportional, which means that when the length increases, the resistance will also increase. And of course, the other side also holds true. When the length decreases, resistance will also decrease accordingly. So when they put all this together, they realize there's a formula that we have here. R equals to rho L over A. This rho here is a constant. We call it the resistivity. Okay? It is a fixed property of the wire's material. So depending on what material it is, the resistivity changes. So if they have the same material, both resistivity are same. Same material, both resistivity are the same. Okay? So what exactly is resistivity? So that's where we're going to go into it. Okay. Okay, sorry, let's go into here first. SI unit for resistivity is ohm meter, because if you go and put this together, okay, R is resistance, the unit is ohm. Cross-sectional area obviously is meter square. Length is meter, so if you strike out like that, you can see the units for resistivity is actually ohm meter. Okay, so that's actually how they derive the units. In case some of you are wondering, how come ohm meter? So you can see here, that's how they go about deriving it. Okay. Now, table 15.3 shows the table shows the resistivity of various materials. Do take note, no need to memorize. Okay, no need to memorize this. Okay, but I need you to know this. Normally, low resistivity will result in lower resistance. Higher resistivity will result in higher resistance. Normally, okay, assuming all other factors stays the same. Same length, same cross-sectional area. But because of resistivity, it can cause a difference in terms of resistance. So typically wires, okay, or we say conductors or wires, okay, we will use low resistivity material. So that's why you realize copper, low resistivity. Good. Tungsten, the resistivity is almost like 3 times, almost 3-4 times. So tungsten not as good as copper, confirm. Okay, so that's why a lot of wires are made of copper. Now, then you can see here, they say, can you suggest why silver is not used to make wires? Silver, actually, the resistivity is better. However, why don't we use it? Because silver is a precious metal. It will be too expensive to use it to make your wires. Can you imagine each wire causing a bomb? A lot of our electrical circuits wouldn't be present in our house already, because every single thing is too expensive. Okay? So take note of that. Next, material high resistivity also can be good. So if you want high resistance, so generally like nichrome is used to make heating coils. Tungsten also high resistivity is used to convert electrical energy to light and thermal energy. So resistivity need not be a bad thing. It really depends on what we call the function. Okay, so obviously wires will use low resistivity, but if you want something to heat up things, that means you want heat to be generated, so you get high resistivity, right? Or you want the electrical energy to be converted to light, another form of energy, you can use tungsten. Okay, so that is for resistivity. It's really a property of material that it tells you that, you know, whether it will result in a higher resistance or lower resistance of the metal. Okay, so work the example 15.9. Do take some time to look through this, okay, because you start to see all the numbers like this, figure out what they're doing here. Okay? It's not very, very difficult, but this gives you a very, very good example of how you can use those values given to you to calculate resistivity, current, resistivity, length, resistance, cross-section area and stuff. So you can go on this. Okay, so key idea, resistance is directly proportional to length, inversely proportional to the cross-sectional area. So before we end, I want to do these little examples with everybody. So example, here I got wire A. We want A. Wire E. Okay, wire E compared to a longer wire F. Maybe I get bigger. Wire F. Okay. Now, this is 1 meter long. This is 3 meters long. The cross-sectional area here is 1 meter square. The cross-sectional area here is maybe 2 meters square. Okay. Now, if I tell you the resistance of this fella, so hey, this guy here, E, initially the resistance is 10 ohm. Okay, so 1 meter wire with a cross-section area 1 meter square, it has a 10 ohm resistance. I want you to find for me what's the resistance of F over here. So how exactly to find? So key idea here, go by proportion. I know some of you say, just use the formula. Okay, you can use the formula to go and find resistivity and then from there substitute the value in, is possible. But there's also a simple way of doing it, which is by proportion. So we take the value of 10 here. Okay, because the wire now is 3 times the length, so I'll multiply this by 3. Because we know R is proportional to L. If the cross-sectional area is double, cross-sectional area is inversely proportional to the resistance. So 3 meters is because of the length, 2 meters square is because of, then I put 3 over 2 because 2 is from the cross-sectional area. Therefore, if you do this, you realize that the resistance of this fella here is now 15 ohm. So learn to use the proportionality. Okay, I don't know whether there's a term called proportionality, but learn to use proportion to calculate the resistance of your wires. Okay, that's why the key idea here is not to calculate resistivity actually. The key idea here is actually to know how you can use proportion to calculate the resistance of a wire compared to the length, compared to the cross-sectional area. Okay, so that is for this last part on resistivity. So hence we have gone through current, we have gone through volts or potential difference or EMF, we have gone through resistance, and the last thing we have gone through a follow-up from resistance is the resistivity. Okay, so these are the 4 things we've gone through in current of electricity. Okay, so this is the map it. You can look through it. These are really just the things we've gone through. So that's all from me today. It's quite a relatively easy-going chapters because a lot of it is purely based on formulas, and generally current of electricity questions are just substitute the values in using the right formulas. Right, so that's all for current of electricity. Let me end my recording.